Alright, during today's lecture, the recording was interrupted for some reason, so the material might be a little bit different than what we covered during the class, but it's essentially going to be the same thing. So today we're going to cover virtual memory, and I hope everyone is caught up with the memory concept before jumping into the virtual memory. So last session we talked about the implementation of paging, how the multi-level paging works. We talked about the two-level paging, how we can calculate the effective access time. Make sure you don't confuse this effective access time with what we're going to cover next session with the virtual memory. And we also, as an example, covered the Intel architecture of implementation of segmentation and paging. Okay, so I saw groups getting created and notification. I hope you're almost done with that. And at this point, you should already be implementing argument passing. Some of you I expect to be done with argument passing. That's why we basically released the project before the spring break, and the lecture discussion session was before the spring break. So during the spring break, you could have time to think about it, or talk to your teammates about the design, or at least without modifying the code, dive into the Pintos code and at least understand the pieces in the process. Let's see. So just take a look at the Project 2 lecture discussions slide and recitation slide. There are some guidance for you how to start, where to start. Also on Piazza. And again, use hexdump for your setup stack function to verify what you have done is correct. All right. So today we're going to talk about the concept of virtual memory. We're going to talk about demand paging and how a page fault can happen and how the operating system can handle the page faults, especially with the implementation of virtual memory. And what are the page replacement? What is the page replacement? A few of the page replacement algorithms. Okay. So basically, what virtual memory is, that it's a separation between the logical address space and the physical available memory on the system, right? So what we talked last session, we talked about the separation of a logical address space of one single process with the physical memory in terms of introducing a mapping of pages to the frames. And we said that okay, if a process has an address space of 32-bit address space, they're not usually using all of that. They only use some of it, and then we're going to just allocate some of the frames in the memory to those pages used by the process, and then we have a page table to keep track of this. And then now we have some frames in the physical memory, and now the process number 1 has some pages, process number 2 has some pages, and process number 3 has some pages. The operating system keeps track of the available frames. It allocates the frames to the pages that are basically for each process separately. Each of them will have a different page table. Now, but still, we didn't speak about a complete separation, meaning even when we're doing this, we're still allocating memory for each process, for whatever each process needs. We are allocating enough memory on the physical memory. But in the virtual memory, the idea is that we only need to bring the part of the program that are needed. All right, not all of it at the execution at any given time. Not all of it is needed, right? And so because of this, we can actually have a much larger logical space than what we have available in physical, right? So an example is that if you have a process that wants to use 1 GB of its address space, for some reason it is a gigantic program and it wants to use 1 GB. And now let's say we have 2 GB or 3 GB of physical memory. Now if there is 2 or 3 of these processes, we will still use mapping between the pages and frames to map some pages of this process into frames. But then after loading the third process, we're done. The physical memory we don't have any available frames anymore, right? So we can't allocate any more frames to any other process. Now the virtual memory idea is that, okay, even though that this process needs or claims to need 1 GB memory, it does not need to access 1 GB at any point of time, right? So the execution, the code is running, in some address in its address space, and there's definitely a lot of data that this process needs. Let's say it wants to render a video, right? But at any given time, at each instruction that is running, it doesn't need the whole memory. So keeping all that data on physical memory on your RAM is just like a waste, right? So for this purpose, we can only bring the parts that are being accessed right now to the physical memory and then leave the rest on the storage, for example. So it allows the address space to be shared by several processes because, again, because of the same mapping scheme, but now we can keep the shared codes on physical memory because we're basically making better use of our physical memory. And it also allows for more efficient process creation. And the reason for that is when we are creating a process, initially like previously, we would say, okay, I have to load this process from the storage disk to the physical memory. So if this process is 1 GB, that takes loading 1 GB of data from the storage to the physical memory and then starting the process. Now, it doesn't make sense because at the start of the process, it doesn't need all of its data. It wants to start its first execution, instructions, and maybe some data, allocated in some of its pages. So now what we can do is that, okay, I'm going to just, allocate, bring a couple of the pages or whatever is needed to the physical memory and then quickly start the process. As it runs, as it goes forward, if it needs some more data, then we'll bring more into the memory, right? We only bring whatever that is required. So this will actually make the process creation more efficient. We also need, there will be also less overhead of adding page table updating because for each page that we are loading from a storage to the physical memory, now we also have to update the page table, right? So this is a diagram for how the virtual memory is working. So we have a physical memory with a limited size. Let's say it's 4 GB, and then our virtual memory is much more than that, right? It can be in hundreds of gigabytes, and the reason for that is that we have the support of the storage, like your hard disk, right? We can store the pages, or technically what we could have as frames on the physical memory. Instead, we would actually store them on the storage, okay, if they're not being used. So, so each of these pages, it can be a map of one page of a process, and that's that's different. But the ones that we bring into the physical memory is a different idea. Now, in order to do that, the goals of this. First, let's go over it. The goals of doing it is that it makes the programmer's job easier, because before this, if a program like the 1 GB process, right, if the process needed to run on a lower memory computer, right, let's say I want to run the same program like a rendering, but on my computer I only have 2 GB, and 1 GB of it is already occupied by the operating system. So the process itself, the programmer, should be flexible. Say, okay, how much memory the system has? Okay, it's 1 GB, so I have to divide and conquer. So as a programmer, I will load some part of my data only to the memory, and I work with it, and then I store it, and then again I load the next chunks or a few minutes of the video, and then I work with it or render it, and then I store it again, right? This is all done by the programmer itself. Store and load from the disk to the memory. Now, here, if the virtual memory is available, I have the illusion that there is no limit in my memory. I can use up to 2 or 4 gigabytes of memory. The 32-bit address space is 4 GB, right? So now I don't know that actually not all of that 4 GB is on the physical memory and accessible to me. I don't care, because I will access it and the operating system handles, if there's a fault. It handles, it loads. That's the job of the operating system. I only see my logical space, and now I don't have to worry about the limit of the physical memory, and I can address anything, and I can work with it. Now, it's the job of the operating system that fits those logical address space into a limited physical space with the backup of the storage. So, as an example, is like when you have a shop and then you have a shelf. Now, you can have a warehouse, which is like much bigger, right? So you can have like tens of bottles, of juice, let's say, in the warehouse, but you keep, some of them available on the shelf. So as the customers come and as they need, you keep refreshing them and updating them, right? So the operating system job is that. It has like a huge storage here, and then it just keeps juggling these frames onto the physical memory as needed, right? So, then this also allows us to basically run more programs, because at any given time we don't have to fit all of the processes, address space into the physical memory. Instead, we only need to bring whatever is needed at execution, which is much less. So that means now we'll have more free space on our physical memory for other processes, so we can increase the number of programs that we run. All right. But if you, at any given time, these programs together may need more DRAM, but not at a given moment. That's the key. We only keep the actively used pages in the DRAM. Okay, not all of it. And then it allows for sharing, right? Because we have like more programs, it also can basically increase the utilization of I/O. And it's one more improvement in the degree of multi-programming. So how we implement virtual memory is either through demand paging and or demand segmentation. Paging is like simpler, and we have like it's easier to understand, and so that's what we're going to like cover today. And this is some part of your project 3. So. Yeah, so let's take a look. So demand paging is that you only page in something from storage to the physical memory like when it's demanded, when it's needed, right? And that's happening through a page fault, right? So when you do that, again, these are all kind of the same concept, but just like different words. So because of this, we need less I/O. So instead of like loading everything from storage to the physical memory, we only bring the pages that are demanded, that are needed. So less storage, reads from the storage. Less memory needed. Again, we are occupying less space in the physical memory because we only bring the demanded pages. And the faster responses, because instead of like loading all of it at this initially and then starting the execution, we only bring the pages that are needed, and so the response to the process can be quick. And again, more users, more processes can run, right? So now let's see what happens. So when a page is needed, we have to reference it. Now, there are a couple of cases that can happen. So before virtual memory, a process used to have a page table, and then there was like its available or allocated pages were always on the physical memory. There was always a page table. There was only like a page table to map these, right? But the process had available or allocated pages, and it could always access those because this page is mapped to this frame. So if the process wants to access this page here, then the page table would be read, then the frame would be basically redirected to the frame, and then the address was there. So now if the process tried to access some place in its address space that was not allocated, let's say for example in the Pintos code above FizzBase, somewhere that is supposed to be like the kernel code, right? If it tries to access it, that page is still allocated, but it's just like illegal. It's out of bounds for this process. Or whether they try to access a page in the, the gaps that were not allocated, that entry is not in their page table. So it's just like, there's, it's illegal. It's out of bounds. And so, we abort the process. Now in demand paging, however, it's different, because the process thinks that, okay, I have these pages, these 3 pages, right? But because we're implementing virtual memory, let's say we don't, because of, the limitation of the physical memory, out of these 3 pages, I only have page 1 and 2 fit into the physical memory. Page 3, I have it on the storage. Okay? So whenever they want to access page number 1 or 2, it's fine, because the page table is there, it's available, in the physical memory, they will redirect it to the correct frame, and then they read it. That's fine. However, if they try to access page number 3, the page number 3 is not available on the physical memory. So, it's kind of like an illegal access, right? So, because, like we will implement it in a couple of slides. We see how it is implemented, but technically it would also consider a page fault. It's kind of the same as they referencing somewhere that is not there, right? Because it's again not available on physical memory. So when this happens, we call it a page fault. And when that page is needed, again, page number 3 is allocated, for process, but it's not available on physical memory. So then the operating system checks in its exception handler and see, okay, where did you try to access? Which page? Is it page 4 or 5, which you're not supposed to access? Then you're supposed to abort, like, the operating system kills the process. However, if you try to access page number 3, and I know that you're supposed to access page number 3, it's just that it's not available on physical memory because of the, implementation of virtual memory, and I wanted to, save up some space on the RAM, so it's not there. So I'm not going to abort you. You didn't do something wrong. Instead, I'm going to load page number 3 into the physical memory and then let you continue, right? So that is when the demand paging is happening. Any page that the process tries to access at the first instance or first time that they try to access that page, the operating system brings it into memory. Before that, it keeps it on the storage. Okay? So for this to happen, we will keep a valid and invalid bit besides the page table, right? Because again, the page table is a mapping between all the address space of the user process and the memory. Now, so in this example, page number 1, 2, 3, they have an entry in this page table, right? So, but it's that for page 3, it's not valid because, it's not available in the physical memory, right? So we actually define one bit, and this bit, if it's like 0, that means that page is not available at that frame. It's not there. And if it's like 1, it means that, okay, that page is valid and you can access that frame. So initially, we set all the pages to 0. It's demand paging, so none of the pages are available on the RAM. So during the address translation, any page access will basically check the page table, and if it's like the invalid bit is 0, that means that page is not loaded in the memory, so then that will cause a page fault, and the operating system will handle it and see if the process is supposed to, it's okay to access that page or not. If it is, then we load it. If it's not, then we abort it. Okay? So this is a diagram for this. So this is the logical memory of the process. Let's say, it has like, from pages from 0 to 7. And the content of these pages is like from A to H. So we already have those stored in the storage, right? All of the process information, data, and execution code, all of it is always on the storage, right? Now, at the load time, we keep loading them into the physical memory. However, in the demand paging, we don't have to do that. So at a given time, let's say, the page table, we have like 3 of the pages on the memory, and this is, their addresses, like frame number 4, 6, and 9. Now, in the page table of this process, we have the entries as this. So entries are like 0, 1, 2, 3, 4, 5, 6, 7. And we have like, page number 0 mapped to the frame 4 and it's valid. Page number 2 is mapped to frame number 6 and it's valid. It's 9, page 3 is 9 and it's valid. The others are invalid. So it's this is blank because we don't care about the number, because there's some zeros and ones there anyways, right? So if you read this, there will be a frame, maybe this frame. But because it's invalid, that means it does not belong to this process. They don't have access. This is not their page. Okay? So that's what the invalid bit does. Alright? So this is very important, and if you understand this and the next couple of slides, this is exactly what's happening during a page fault. It might show up like, a test. So make sure that this is like clear. So a CPU tries to access a logical address, right? So normally what we used to have was that, okay, we have a page number or page index, and the page index is getting looked up at the page table. There would be a frame, and then we add the offset of this logical address, and then, reference that physical address. Now, in this case, if the page table, like page index, was out of bound, or it was not in the page table, then we would like say, okay, you're accessing something that you're not supposed to. In a virtual memory, it's different, because this page might be still in the bounds of the process. However, it might be not valid. If it's valid, the same thing happens. That means that frame is available in memory, and that page, can be accessed. If the valid bit is 0, that means that the page that you're looking for is yours, but it's not in the physical memory, in the RAM. Instead, it's somewhere in the disk. So the operating system through a page fault interrupt brings those pages from the disk to the physical memory, updates this table, and then starts over. Okay. So when there is when the page fault happens, that means again like a reference that is to a page that is not in the memory. Either it's like illegal, or it's just like not there because of the virtual memory. So in the page fault, the OS looks at another table in the PCB to decide. This is a typo. To decide if it's an invalid reference. That means this is a page that is not. It does not belong to the process, which in that case, like if we abort it. If it's a valid reference, so it basically resides in one of the pages that are allocated to that process, but it's just like not on physical memory, we swap in. That's what we call. We swap in, meaning we bring stuff, or those pages, from storage to the physical memory, right? After we swap in order to do that, first of all, we find a frame in the physical memory which is available, that is not mapped. Remember, the operating system also keeps track of all the free frames, right? So we pick a free frame, and then we read the page from the disk into this. We load this into a frame, and now we update the page table of that process to basically indicate the change and say, okay, now your page is valid, and now it's in this frame, and then we restart that instruction that caused this page fault. Okay. So here again is the diagram. Make sure you understand all the steps. This is an example of a page fault happening and swapping in, and also swapping out. So we're going to talk about it in a couple of slides. But if we need to like make some space, if there is no available frames, we should basically pick a frame and swap it out and store it on the disk so that we can swap another one in. Okay. So in this case, the process again tries to access a reference to memory. That memory gets looked up in the page table. Now the page table, we check the validity bit. If it's invalid, then that's a trap, that's the page fault. The operating system takes control. The operating system takes a look at the page table, and obviously at this point, in this example, we don't want to abort the process, but it's just like that its allocated page is not in the physical memory. So we take a look at the storage disk. If we need to, we swap out, and if not, the free frame is already there. We just bring that missing page from the storage back to the free frame, and then once it is available on physical memory, we have the frame here. We update the page table based on this. We set the validity to valid, and then we restart the same instruction. So this time, when they try to reference it, it's valid, and then it's in the frame. So the page table redirects that memory access to the physical memory. All right. So this summarizes it. So as I said, like if the frames are not available, we have to replace some of the pages. That means we have to find a page and swap it out to make some free space in the physical memory, right? So, and there are algorithms to do that, because like, you know, among these pages that are available on physical memory, which one we should like pick, which one we should like throw out. And there are different criteria. So for example, we want an algorithm which will result in minimum number of page faults, because each page fault now will cause a swap out or a swap in, and then that includes I/O, and that's slow, and that's like overall this is running, you know, in the page fault handler, which is like overhead. So we don't want to minimize those. And because of, you know, there's no optimal algorithm, we don't know what the, you know, behavior of the process is. You know, a page might not be used, so we try to, you know, get rid of it and store it back on the disk. But again, the process might try to access it, so we have to bring it in. And again, at some point we might decide, okay, this page is not used anymore, so we store it back into disk, and again at some point we bring it back, right? So this can happen multiple times. So in order to do this, what we need to do is basically store the pages to the disk, and then we bring the new pages down to the physical memory. Now remember this, each of them consists of a I/O, like storing to the disk or reading from the disk, but there's also a difference. So if I want to swap in, I'm reading from the storage and then, you know, writing into the physical memory, which is already very slow. Now swapping out is even worse, because now I'm writing to the disk, which is usually much slower, right? So, but we don't always need to do this, right? So if I load a page from the disk, the disk to the, you know, frame, so I make a copy. So this page already exists on the disk storage. Now, if this page is untouched, maybe it was just like a piece of code. Usually code doesn't, you know, change, right? So now if this piece of code, this page is not changed, does it make sense that I overwrite what was there already with this one? Basically, it does not, you know, it doesn't make sense. So I only need to replace that page with the, you know, this copy if it has changed. If it has not changed, I can just like drop it. So this is what we call the dirty bit or modify bit. This is again important to know about this page replacement. So for each page, I can assign a dirty bit to it, and then I can take a look. Once I bring a page to the memory, it's not dirty, it's clean. No one has like, you know, modified anything in it yet. As soon as a process, you know, tries to access it and write something to it, then this page is now dirty. It's modified. So at the time of replacement, I can take a look. Is this page modified or not? If it has not been modified, I don't have to actually swap it out, and I can save some time. Instead, I can just drop it. It's the same as that. But if this page is dirty, then it's modified. If I just drop it, then I will lose data. You know, I don't have the updated information on the disk. So then I have to actually swap it out and save it. Okay, so this is handled by this. So we only write the modified pages. And then with the, you know, when we implement the replacement completely, then the separation between the, you know, logical memory and physical memory is done, and you can actually have larger virtual memory on limited physical memory, because you can just like keep moving things around, and that's the job of the operating system. All right. And this happened in the page fault service routine. So, simplified steps, one more time. Find the location of the desired page on the disk when you want to swap it in. Find a free frame. If in the physical memory you can find it, then you can use it. If not, you find a victim, one of the pages that you want to swap it out, and make some free space, and then read the desired page into the new frame, and then update the page table for the process. This also might be two processes. Remember, when you're swapping it out, you also have to update the page table. So this can be either from the same process or a different process. Let's say if user 1 or process 1 has some pages in memory, right? If it's not using this page anymore, and I want to swap it out, then I have to update the page table for process 1 because I swapped it out. And then I swap in a different page and I update the page table again. But also, the operating system might also use another process's pages. So let's say we have two processes, and process number 2 is, keeping many pages on the physical memory but not using them anymore. Now process number 1 needs a page. So, I don't have free space here, so I pick one of the pages from process 2, I swap it out, I update process 2's page table, because that page that was here, it's an invalid anymore. It's not valid anymore. So, when I bring a page for process number 1 here, I update page table for process 1. If I don't set the page table of process 2 thinks that it is a page which is allocated to process 2, so it try to access it at some point, and then it will actually read or modify the data that is actually process 1's, right? So it's just like that, the operating system needs to take care of all the page tables. So during a replacement, this is the page table. In this example, we're just talking about like one process. So the frame frame entry or the page table entry, we have the frame address here and an invalid bit here. So when the victim is picked in the physical memory, then we page it out to the disk again, considering it's dirty. If not, we can skip this. Then we're gonna go here in find that page entry here and then mark it as invalid. Then we load the new page from the disk to the physical memory. We make a copy, and then we update the page table based on that. We put the new frame address to that entry and also mark it as valid. Okay? So now, in order to do this, there are multiple algorithms, and one thing to remember is that we want lowest page fault. All right. So we're gonna go through a couple of examples. In all of the examples, what we have here is a reference string. So first of all, we're not gonna talk about multiple processes, and also we're not gonna have the whole diagram of physical memory. Instead, what this process is doing is that it tries to access a memory an address within the page number 1. The offset doesn't matter anymore, right? It tries to access its page number 1, whether it's available in memory or not. Then it tries to access some memory address within page 2. Then it will try to access some address in page 3. Then 4, then 1. So this is called a reference string, right? And then we keep track of the pages that are available on physical memory, and then we take a look at the example. All right. So I'm going to jump into this and come back to that slide. So here is an example. So we have the reference string, and let's say we have physical memory very limited with 3 frames, and then so at any given time 3 pages can be in the memory. But which 3? So let's see. So the first algorithm is FIFO, meaning the first page that you bring into the memory is going to be your first victim, right? The older one, basically, that you bring in is going to be the first one that is going out, right? So this is usually the table that we work in. So this is the reference string. This is time, And this is frame number 1, frame number 2, frame number 3 available in physical memory. And now this is what pages that they keep. So initially, all of them are like 0, right? And our next victim, or basically the frame that we want to update or replace, is going to be like this one, right? So when we access the first entry in the string, it's page number 1. Do we have page number 1 in here? No. So we have to bring it. So we already have a free frame here. So I'm going to just load the page number 1 into here in the page fault handler, and then our victim is going to be next time. So next access is page 2. Do we have it in the page table here? No, we don't. So bring it into the entry and move the arrow down. So next reference is page number 3. Do we have it in the page table here? No. So again, we replace it here, and now the page table looks like this. At this point, we don't have any more free frames, and our victim, who's going to be selected because of the FIFO, is the first one that we brought in. Because we brought 1 first, so our victim is going to be this one. So when we access page number 4, do we have it in the page table? 1, 2, 3? No, we don't have it. So we have to bring 4. Who is the victim? Number 1. So that's why we replace this one. And then the arrow keeps going. Now among these, the 2 is the first in line, right? So the next reference would be number 1. We just swapped it out, but that's what it is, right? So we will replace the 2 with 1. And as we go, this happens. So we replace 3 with 2, we replace 4 with 5. Here, reference to 1, we actually have it in the page table, so there is no replacement, there is no page misses. And so again, 2 is also there, but 3 is not, so we have to replace it. Then 4 is not there, the 5 is there, right? So when a reference page is available, it's called a page hit. When it's not there, it's a page miss. Now, in a case of when we have a free frame in a page miss, we only load the page to the physical memory. If we have to evict one of the frames, that's also a page replacement. So in this case, in this example, we had like 1, 2, 3, 4, 5, 6, 7, 8, 9 times we had a page fault, and for the first 3 times we had available memory, we had free frames, but for 6 of them we have to replace pages. Now, an idea is that as I increase the page, as I increase my physical memory, the available frames, I would probably have less issues, right? That just makes sense. More space, that means like I can keep more frames. So this is what you expect. As you increase the number of frames, you would expect the number of page faults would, reduce. But that's not necessarily happening in this example. So let's see, the same reference string, and instead of like 3 frames, now we have 4 frames. So if you solve it, again, you bring 1, 2, 3, 4 the first times, and then the 1 you have access to, 2 you have access to, 5 it's not there, you replace, and then 1, because you just swapped out 1, you replace it, but again you just swapped out 2, so now you will bring 2, and then again you just replace page 3 with 2, but now you try to access it, and then so in this example it's just like a little weird, but because of the order of the page references that we didn't know, we actually ended up like with 10 page faults. So this is called something like, which is named Beladi's anomaly, which is like, you add more frames, but you have more page faults. So this is not like expected, and it's not like, typical, but it happened in this case because we didn't actually use any information. So we just, the FIFO just kept moving the arrow, but also obviously the order of the page reference. So with a different page reference string, it could like, the result would change. So, this normally would not, like again, the FIFO algorithm is not good in this case, alright? Let's talk about this here. So, the good thing about FIFO is like it's simple and, it's easy to implement. So you just like have the, tail of the list and then the head of the list. And then it might be good because the one that was brought in the longest ago might not be used anymore. But it might also be very bad because whatever that was like, brought a long time ago, it might be just like, the processes might be using it, frequently. So it's just like no information we're not using. The time that it was like brought to the memory doesn't give us useful information, right? So it suffers from the abilities anomaly, and the performance of FIFO is not good because usually when a process, brings a page, they might want to keep working with them, in the near future as well. So there are a family of algorithms which are called, I think, stack algorithms, and those are basically different than FIFO. So in FIFO, when we change the number of frames, the whole thing changed, right? But the stack family of algorithms, they're like that. If you increase the number of frames at any given time, you would have the same pages, but maybe one more, right? So in this case, for example, let's see. So if you have 3 pages, 1, 2, 3, 4, here. Now it's 4, 2, 3. So this is very different than this. So in the stack ones, it's that if you have 3 pages, your algorithm picks something. If you have 4 frames, you would have the same 3 frames, same 3 pages, but also another one. So in this case, you wouldn't have the Baladi's anomaly because, it will be proven that it will work at least as well as the 3 one, the smaller one. So, let's see. Next is the optimal solution. So the optimal algorithm, if you remember something like shortest job first, is looking into the future. It replaces the page that will not be used for the longest time in future. So if a page is going to be accessed in the near future, I'm not going to replace that. Okay, that doesn't make sense. If we have a page that is our previous example, we were just evicting a page that was just about to be accessed again. So, if I look into the future and have an idea that who's not going to be used, in near future, I can, it is basically optimal. So in this case of the 4 frames, again, the first 4 is of course they're going to brought in. And then, at this point, 1 is there, 2 is there. When 5 is going to, when the 5 is accessed, I'm going to take a look at, the access time. I have 1, 2, 3, and 4 in the page table. And amongst these, 1 is accessed here, 2 is accessed 3, and here and 4. So 4 is the one that I'm not going to access soon. So I'm going to replace the 4 with 5. And then here, again, the 5 is going to be not accessed soon. And then, after here, we're not having any access, so the arrow just keeps moving forward. But the idea is basically the same. So in this case, we only have 6, and remember, this is the first 4 is just inevitable. So it is proven to be optimal. The problem is that we don't know the future, right? The same as shortest job first. We might come up with approximations. But what is it used for? So first of all, it's used as a reference to compare other algorithms. So although it is actually impossible, but if we have, the reference string, then we can basically use it as a benchmark for other algorithms. If your algorithm's performance is close to the optimal, that means you're doing a pretty good job. Okay? So it's proven to be optimal with the lowest fault rate. Again, the same as the shortest job first in the CPU scheduling. And but we can't actually implement it. So is there any practical best algorithm? No, because it all depends on the future accesses which you don't know, right? So can we do something terrible? Yes, you can just random replacements, but apparently similar or semi-random things are used. So this is just interesting to know. Alright, so next algorithm is LRU, which is least recently used. So instead of, looking into the future, it would actually look into the past and say, okay, I'm going to replace a page that has not been used for the longest amount of time. So the idea is, if a page is, not used recently, it's maybe just like forgotten. Maybe no one wants to use it anymore, right? So, but if a page is recently used, chances are that it is still in the, workspace of a process, and they want to like access it again. We're going to talk about it probably next session. Accesses to the memory is both, spatial and temporal, kind of dense. So, if a process is like in accessing one page, let's say if it's a code, right? Maybe they're in a loop, right? So they keep running instructions within that loop, right? So they keep accessing to the same page. Or if they want to work with some data, like let's say in a matrix, right? They want to keep moving things around. So they want to like keep accessing in the same. And then once they're done with this routine, then they will probably jump to a different page, and then they keep working there. So that's how, it's kind of, distributed. So LRU looks in the past. So let's say after the 4 pages here, amongst the 1, 2, 3, 4, at this given point, the 1 is the least used in the past, right? So this is the one that we're going to evict. But unlike FIFO, when a page is referenced, this is not the oldest anymore, but it's recently used. So it's not going to be our victim anymore. So at this point, we have like 1, 2, 3, 4 in our page table. But between 1, 2, 3, 4, 1 is here, 4 is here, 3 is here, 2 is here. So 2 has been used least in the past. So that's going to be here. And we're not replacing anything yet. This is just the victim indicator, right? And then 2 is now getting accessed again, right? So now this is being used recently. So 3 is the one that is not. So when we bring the 5, we actually replace it with 3. Again, we might access 3 right away. We don't know the future, but we have an idea that we can look at the past, have an idea about the future. So in this example, the LRU actually have 8 page faults. So again, obviously, it depends only on the reference string. So again, it's just like guesses the future based on the past experience, and the difference between LRU and the FIFO is that FIFO was looking at the timestamp that the page was brought in. The LRU is looking at the timestamp that the page is accessed. So whenever a page is accessed, it's just like, refreshed. And so to be perfect, you must have a timestamp for each of the pages and, update them based on each reference. So each reference to a page, you have to update the timestamp of that. And then whenever you want to pick the longest one, you have to either have look for it or have it sorted some way. And this is too costly. You can't this is takes a lot of overhead. Think of it. We're just talking about memory reference. For each memory reference, if you want to change anything, that's just it's basically, you can't use your computer, right? So because of this, you want an approximation to implement LRU, okay? So this is one actual implementation of LRU, which is like a stack implementation, right? So you keep the page, the reference pages in a double linked stack, and so as you basically access each page, you bring that page to the top of the stack, right? So then the one at the bottom would be, the one that is recently used. So let's say at this point of time, at point A, we have 2 at the top, and then 1, and then 0, and then 7, and then 4, right? So when 7 is accessed, you basically, it's a double linked list. So there's a linked list there's a link, a pointer from this to this, from this to this, and also from this to this, and from this to this. And then you also have the top of the stack. So when 7 is accessed, you bring it up. you don't move things around, you just like play with the pointers. So instead of like 4 pointing to 7, you change 4 pointing to the 0, and then also vice versa. And then instead of like 7 pointing to 4, you point it to 2. So then you basically bring it up to the top of the stack. But this requires modifying 6 pointers, so it just like doesn't make sense. All right. You don't need to search for anything, but it's still expensive. So how about the approximation? So one idea is that I actually define a reference bit. So for each page, I define a reference bit, and anytime, like initially it's 0. That means I brought it in the memory for the first time, but it hasn't been used again. So if a page is referenced again, I will set the reference bit to 1. So when I look at the pages, if a page is, has the reference bit as 1, that means it has been used since we brought in, right? So, but if the page is 0, the reference bit, that shows that, since the time that we brought them in, no one has used them anymore, so, they're not recently used. But it's like also not very clear. First of all, we do not know the order. So amongst the pages that the reference bit is 0, which one is older? Because that's supposed to be the victim, right? Or let's say if all of the pages are accessed 1, so all of the reference bits will turn to 1, right? So which one of them are older now? Which one of them is least used? So we don't have that, right? We don't have the information. So one idea is to actually define an additional bits. Instead of like having 1 bit, we define, for example, a byte, right? And this byte is like, it shows the history of references. So that means that this, like most recently, I have accessed this, and then a time, like an access before that, also I accessed this. A time interval before that it was not accessed. A time interval before that it was not accessed. Before that it was accessed and then not. So how does it keep the history? At the time intervals, we, not at each like reference, but at some intervals, we basically shift this to the right. Right? If we shift to the right, So if we shift to the right, then this will be the oldest value, and that will be lost. So this will be dropped, and now we enter from the left a fresh information. So if within the time interval this page has been accessed, then I will enter a 1. If within the time interval this page has not been accessed, I will enter 0, right? The same basically reference bit that we had, we enter and then push the rest of them. Now, what does it do? Basically, if you look at this number as an integer, the larger the number, that shows that the more recent it has been used, right? Because in the closer time intervals to this moment, they have been referenced, right? Whereas the smaller the number, that shows, recently in last interval, or the one before that, they were not referenced. So each bit, gets its, value based on, history. So obviously this is the most important bit. It's the highest bit, right? So that's just like the immediate interval before this. If you want to compare the pages that all of them have like 1 here, or all of them have 0, then you look at the next bit, which is the interval before that. Then you look at the interval before that, right? So it's kind of like, comparing the different words in dictionary, right? So this is with multiple bits. Now, there is another algorithm that we didn't finish today in the lecture, so I'm going to go talk about it in Thursday's lecture, and that is called a second chance. So I would still ask you to take a look at, this. At least that will help us take the pace. We'll cover these slides then. And there are a couple of counting algorithms, which again we just keep increasing their references, and then We have least frequently used and most frequently used. We may again talk about them on Thursday. And so this is the exercise that I ask everyone to do. So this one we already have covered, the LRU, LFU, in optimal page. Well, the LFU we didn't cover, but you can basically just keep counting the numbers. But anyway, so this is an exercise that will help you understand. You have like 4 frames. This, you have this string reference. It's different than the previous one. And, just try to take one at a time, just like how we did in class. And then find the number of page faults in total. The number of page hits. This is basically the page hits and faults are all the references all together. And then amongst the page faults, the first ones that we have free frames, there won't be any replacements, but the ones that we don't have available free frames, there will be replacements for them. All right. And after this, there's exercise for the LRU clock, which we're hopefully going to cover next session. And so for next session, keep working on your design document. The due date is this Friday, April 5th. Make sure that you are, finishing argument passing, because there are a lot to do for the next level project. So we don't want to, again, get stuck and have a lot of work at the, close to the deadline. So let's meet the micro deadlines. And this is the last time I'm asking, if anyone has not filled in the PA survey, I would actually, appreciate if you do it. Look for the announcement on Piazza. I'm not going to make so many announcements in class anymore. And also for recitation, slides, anything that is related to project, it will be on Piazza. So look for it, especially the posts that are either endorsed by the instructing the staff, or the posts that are from the instructing the staff. Look for those. All right. So to next session, we're going to continue with the LRU approximations and a couple of other things regarding the virtual memory. All right. So see you now on Thursday.